How step-up transformer work. A step-up transformer is a type of electrical transformer that increases the voltage of an alternating current (AC) power supply. It is designed to have more turns on the secondary coil compared to the primary coil, resulting in a higher output voltage than the input voltage. Basic construction: a transformer consists of two coils of wire, known as the primary coil and the secondary coil, wound around a common magnetic core. The primary coil is connected to the input voltage source, while the secondary coil is connected to the load. Basic construction. The basic construction of a step-up transformer includes the following components. Core. The core is typically made of a high-permeability material, such as laminated iron or steel, which provides a low reluctance path for the magnetic flux. It forms the central part of the transformer and helps to concentrate and direct the magnetic field. Primary coil. The primary coil is a winding of insulated wire connected to the input voltage source. It is wound around one section of the core and consists of a specific number of turns based on the desired voltage transformation ratio. The primary coil generates a magnetic field when an alternating current flows through it. Secondary coil. The secondary coil is another winding of insulated wire, separate from the primary coil. It is wound around another section of the core and typically has a greater number of turns compared to the primary coil. The secondary coil is connected to the load and generates an induced voltage based on the magnetic field produced by the primary coil. Insulation. Both the primary and secondary coils are insulated from each other and the core to prevent electrical short circuits. Insulating materials, such as enamel or varnish, are used to coat the wire windings and provide insulation between the layers of the coils. Terminals. The primary and secondary coils have two ends each, known as terminals, which allow for the connection of external electrical circuits. The primary coil terminals are connected to the input voltage source, while the secondary coil terminals are connected to the load. Protective enclosure. Transformers are often housed in protective enclosures or casings made of materials like metal or plastic. These enclosures provide insulation, mechanical support, and protect the transformer from environmental factors. Cooling system. Transformers generate heat during operation, and larger transformers may incorporate cooling systems to dissipate the heat and maintain optimal operating temperatures. Cooling methods include natural convection, forced air cooling, or liquid cooling using coolants like oil. The specific design and construction of a step-up transformer may vary depending on its intended application, power rating, and voltage requirements. Transformers can be found in various sizes and configurations, ranging from small devices used in electronics to large units used in power grids. Turns ratio. The turns ratio of a transformer is the ratio of the number of turns in the secondary coil to the number of turns in the primary coil. It determines the voltage transformation ratio between the input and output sides of the transformer. The turns ratio is typically represented as NP/Ns or NP/Ns, where NP is the number of turns in the primary coil, and Ns is the number of turns in the secondary coil. For a step-up transformer, the turns ratio will be greater than 1, indicating that the secondary coil has more turns than the primary coil. The turns ratio directly affects the voltage transformation between the primary and secondary coils. The voltage ratio is inversely proportional to the turns ratio. In other words, if the turns ratio is 1 to 2, the secondary voltage will be twice the primary voltage. Similarly, if the turns ratio is 1 to 3, the secondary voltage will be 3 times the primary voltage. For example, suppose a step-up transformer has a turns ratio of 1:10. If the primary coil is connected to a 120-volt AC power supply, the secondary coil will produce an output voltage of 1,200 volts. The actual voltage transformation also depends on the input voltage frequency and the design of the transformer, including factors such as core material and winding configuration. It's worth noting that while the turns ratio determines the voltage transformation, it also affects the current transformation. According to the principle of conservation of power, as the voltage increases, the current decreases in proportion to maintain the same power level. Magnetic induction.
Magnetic induction is the process by which a changing magnetic field induces an electric current in a conductor, as described by Faraday's law of electromagnetic induction.
In the context of a transformer, magnetic induction is the fundamental principle behind the functioning of the device. When an alternating current, AC, flows through the primary coil of a transformer, it creates a changing magnetic field around the coil. This changing magnetic field induces an electric current in the secondary coil through the phenomenon of magnetic induction. The alternating current in the primary coil generates a magnetic field that expands and collapses around the transformer's core. As the magnetic field expands and contracts, it cuts across the turns of the secondary coil. According to Faraday's law, this changing magnetic field induces a voltage in the secondary coil. The induced voltage in the secondary coil is directly proportional to the rate of change of the magnetic field, the number of turns in the secondary coil, and the time for which the magnetic field lines cut across the coil. The relationship between the induced voltage, the rate of change of magnetic field, and the number of turns is described by Faraday's law. V equals ns asterisk d phi/dt. Where V is the induced voltage, ns is the number of turns in the secondary coil, d phi/dt is the rate of change of magnetic flux. Magnetic induction is a key concept in transformer operation, as it allows for the efficient transfer of electrical energy from the primary coil to the secondary coil. By changing the number of turns in the coils, the voltage can be stepped up or stepped down, depending on the application requirements.
Voltage transformation.
Voltage transformation refers to the process by which a transformer changes the voltage level of an electrical power supply. A transformer can either step up or step down the voltage depending on the turns ratio of its coils. In a step-up transformer, the number of turns in the secondary coil is greater than the number of turns in the primary coil. As a result, when an alternating current, AC, flows through the primary coil, a magnetic field is created which induces a higher voltage in the secondary coil. This voltage is proportional to the turns ratio of the transformer. For example, if the turns ratio is 1:10, the secondary voltage will be 10 times higher than the primary voltage. Conversely, in a step-down transformer, the number of turns in the secondary coil is fewer than the number of turns in the primary coil. In this case, the induced voltage in the secondary coil will be lower than the primary voltage. The voltage transformation occurs through electromagnetic induction. When the magnetic field generated by the primary coil expands and collapses, it cuts across the turns of the secondary coil, inducing a voltage in the secondary coil according to Faraday's law of electromagnetic induction. The voltage transformation in a transformer is based on the principle of conservation of energy. Since the power, P, in an electrical circuit is given by the equation P equals V times I, voltage multiplied by current, the transformer adjusts the voltage and current in such a way that the product of the voltage and current on the primary side is equal to the product of the voltage and current on the secondary side. Voltage transformation is a crucial aspect of electrical power transmission and distribution. Step-up transformers are used in power plants to increase the voltage for efficient transmission over long distances, while step-down transformers are used near the point of consumption to decrease the voltage to safe levels for appliances and equipment.
Load connection.
Load connection refers to the process of connecting an electrical load or device to the secondary coil of a transformer. The load is the component or system that consumes electrical power from the transformer. In a transformer, the primary coil is connected to the power source, while the secondary coil is connected to the load. The load can be any electrical device, such as lights, motors, appliances, or an entire power distribution system. When the load is connected to the secondary coil, the induced voltage in the secondary coil is utilized to power the load. The load draws electrical current from the transformer, converting electrical energy into other forms such as light, mechanical work, or heat, depending on the nature of the load. It's important to ensure that the load connected to the transformer is within the transformer's power rating and voltage range. Exceeding the rated capacity of the transformer or connecting a load with a significantly different voltage requirement can lead to inefficient operation, overheating, or damage to the transformer and the load. In power distribution systems, transformers are used to step down the high-voltage transmission lines to lower voltages suitable for consumer use. The load connections are made at distribution transformers, where the step-down voltage is fed to residential, commercial, or industrial areas. The connection between the transformer and the load can be established through electrical wiring, cables, or busbars, depending on the specific application and system design. The load should be properly connected, following electrical safety guidelines and regulations, to ensure reliable and safe operation of the electrical system. Overall, load connection is a critical step in utilizing the voltage transformation capabilities of a transformer, allowing electrical power to be efficiently delivered to various devices and systems for their intended operations. Step-up transformers are commonly used in power transmission and distribution systems to increase the voltage for long-distance transmission, as higher voltages reduce power losses. They are also used in various industrial applications and electrical equipment where higher voltages are required. It's important to note that while a step-up transformer increases voltage, it reduces current proportionally due to the conservation of power. The power, P, in a transformer is given by the equation P equals V times I, where V is voltage and I is current. As the voltage increases, the current decreases to maintain the same power level.